Hello, welcome to Chapter 5, which will cover physical equilibria of pure substances. So, boiling, freezing, and the conversion of graphite to diamond are all examples of phase transitions, which will be the topic of this chapter, which are changes of phase without change of chemical composition. Many phase changes are common everyday phenomena, and their description is an important part of physical chemistry. They occur whenever a solid changes into a liquid, as in the melting of ice, or a liquid changes into a vapor, as in the vaporization of water in our lungs. They also occur when one solid phase changes into another, as in the conversion of graphite into diamond under high pressure, or the conversion of one phase of an iron into another as it's heated in the process of steel making. The tendency of a substance to form a liquid crystal, for example, is a distinct phase with properties intermediate between those of solid and liquid, guides the design of displays for electronic devices. Phase changes are important geologically as well. For example, calcium carbonate is typically deposited as aragonite, but gradually changes into another crystal form, calcite. So, the Gibbs energy, G, which is defined by G equals H minus Ts, of a substance will be at the center stage of all of our following discussions. We need to know how its value depends on the pressure and temperature. As we work out these dependencies, we'll acquire a deeper insight into thermodynamic properties of matter and the transitions it can undergo. So let's talk about conditions of stability first. First, we need to establish the importance of molar Gibbs energy, G sub n, in the discussion of phase transition of pure substance. G sub m, or molar Gibbs energy, is simply the Gibbs energy of a substance in totality divided by the number of moles of that substance, n. The molar Gibbs energy, an intensive property, depends on phase of the substance. For instance, the molar Gibbs energy of a liquid water is in general different from that of water vapor at the same temperature and pressure. When amount n of the substance changes from phase 1, which could be a liquid, with molar Gibbs energy of G sub m1, to phase 2, the vapor, for instance, with a molar Gibbs energy of G sub m2, the molar change in Gibbs energy is defined as the following, where delta G is going to equal the number of moles of substance times the molar Gibbs energy in the second phase minus the number of moles of substance times the molar Gibbs energy in the first phase. And we can simplify this calculation by pulling the number of moles, n, out to the front and looking at n times the difference between the molar Gibbs energy between the two phases, 2 and 1. We know that a spontaneous change at constant temperature and pressure is accompanied by a negative value of delta G. We've seen this before. This expression shows, therefore, that a change from phase 1 to 2 is spontaneous if the molar Gibbs energy of phase 2 is lower than that of phase 1. In other words, a substance has a spontaneous tendency to change into the phase with the lowest molar Gibbs energy. And this is congruent with our previous discussions of how everything in nature tends towards stability of lower energy states. Lower energy is synonymous with greater stability, and therefore spontaneity of reactions are defined by seeking the most stable, lowest energy state. Let me clean this up a little bit. If at a certain temperature and pressure, the solid phase of a substance has a lower molar Gibbs energy than its liquid phase, then the solid phase is thermodynamically more stable, and the liquid will, or at least will have a tendency to, freeze. If the opposite is true, the liquid phase is thermodynamically more stable, and the solid will melt. For example, at 1 atmosphere, ice has a lower molar Gibbs energy than water in its liquid form when the temperature is below 0 Celsius, and under those conditions, water converts spontaneously to ice. Conversely, if the temperature at 1 atmosphere is above 0 degrees Celsius, water will spontaneously tend to melt into the liquid form because that phase has a lower molar Gibbs energy. So let's take a look at how the variation of Gibbs energy occurs in conjunction with pressure and then with temperature. To discuss how phase transitions depend on pressure, we need to know how molar Gibbs energy varies with pressure. So this chapter is rich with derivation, and I encourage you to get into the chapter, look at the derivations, and try to understand the rationale for how we achieved these relationships we're going to discuss. But for the context of this lecture, we're just going to simply reference the derived equations and rationalize them. So, for context, we show in the derivation 5.1 in the text that when the temperature is held constant and the pressure is changed by a small amount, delta P, the molar Gibbs energy of a substance changes by the following quantity, where change in molar Gibbs energy, delta Gm, equals the molar volume times that change in pressure. So this expression is valid when molar volume is constant in the pressure range of interest. What this equation tells us is that because all molar volumes are positive, the molar Gibbs energy increases when pressure increases. We also see that for a given change in pressure, the resulting change in molar Gibbs energy is greatest for substances, with large molar volumes. Therefore, because the molar volume of gas is much larger than that of condensed phase, either liquid or solid, the dependence of molar Gibbs energy on pressure is much greater for a gas than for a condensed phase. For most substances, with water being a very important exception, the molar volume of the liquid phase is greater than that of the solid phase. Therefore, for most substances, the slope of the graph of molar Gibbs energy against pressure is greater for a liquid than for a solid. And we see these characteristics illustrated in figure 5.1. So let's take a quick look at figure 5.1 over here. We can see that the region where the molar Gibbs energy of a particular phase is least is shown by a dark line, and the corresponding region of stability of each phase is indicated by shading. So at these junctions on the x-axis, we have transitions from a very light shade to an intermediate shade to a darker shade, and the lightest shade is where gas is most stable. Liquid is most stable in the intermediate shading, and in the darker shading, solid is most stable. Now, note also that we have these nice linear relationships with liquids and solids, with an intersection which defines that phase transition here and the phase transition here. But also notice that the relationship for how molar Gibbs energy varies with pressure is nonlinear for gases, which we'll get into in slightly more detail here in a second. So as we see in figure 5.1, when we increase the pressure on a substance, the molar Gibbs energy of the gas phase rises above that of the liquid, then the molar Gibbs energy of the liquid rises above that of the solid. Because the system has a tendency to convert into the state of lowest molar Gibbs energy, the graphs show that at low pressures, the gas phase is the most stable. Then at higher pressures, the liquid phase becomes more stable, followed by the solid phase. In other words, under pressure, the substance condenses to a liquid, and then further pressure can result in the formation of a solid. We can use equation 5.1 to predict the actual shape of the graphs, like we see in figure 1 as well. For solid or liquid, the molar volume is almost independent of pressure. So 5.1 is an excellent approximation to the change in molar Gibbs energy, and with that we can determine the following, where the molar Gibbs energy times the final pressure equals the molar Gibbs energy times the initial pressure plus an adjustment factor of the molar volume times the difference between final and initial pressures. This equation shows the molar Gibbs energy of a solid or liquid increases linearly with pressure. However, because the molar volume of a condensed phase is so small, the dependence is very weak, and for typical ranges of pressure normally of interest to us, we could ignore the pressure dependence of G. The molar Gibbs energy of a gas, however, does depend on pressure. And because the molar volume of gas is large, the dependence is significant. With that, we have another derivation, shown below, where the term which includes the molar volume is replaced with RT/ln Pf over Pi. This equation shows that molar Gibbs energy increases logarithmically as a natural log of pressure, with the increases logarithmically with pressure. The flattening of the curve at high pressures reflect the fact that V sub m, or the molar volume, gets smaller under pressure, and therefore the molar Gibbs energy becomes less responsive to pressure. And that's what we're seeing here and here, where you have a logarithmic relationship that tends to flatten out as the pressure increases. Now, let's take a look at how Gibbs energy varies with temperature. Now we consider how molar Gibbs energy varies with temperature. For small changes in temperature, we show in derivation 5.3 that the change in molar Gibbs energy at constant pressure is the following. Delta G sub m, change in molar Gibbs energy, equals negative molar entropy times change in temperature. This expression is valid provided the entropy of the substance is unchanged over the range of temperatures of interest, or changes trivially over the range of interesting temperatures. Equation 5.4, the one we just showed, tells us that because molar entropy is positive, an increase in temperature results in a decrease in molar Gibbs energy. We see that for a given change of temperature, the change in molar Gibbs energy is proportional to the molar entropy. For a given substance, there is more spatial disorder in the gas phase than in a condensed phase, so the molar entropy of the gas phase is greater than that of the condensed phase. It follows that the molar Gibbs energy falls more steeply with temperature for a gas than for a condensed phase. The molar entropy of the liquid phase of a substance is greater than that of its solid phase, so the slope is least steep for a solid. You see this in figure 5.3 summarizing these characteristics. Figure 5.3 also reveals the thermodynamic reason why substances melt and vaporize as the temperature is raised. At low temperatures, the solid phase has the lowest molar Gibbs energy and is therefore the most stable. However, as the temperature is raised, the molar Gibbs energy of the liquid phase falls below that of the solid phase and the substance melts. At even higher temperatures, the molar Gibbs energy of the gas phase plunges down below that of the liquid phase and the gas becomes the most stable phase. In other words, above certain temperatures, the liquid vaporizes to gas. And take a look at figure 5.3 here, where on the y-axis we have molar Gibbs energy, and on the x-axis we have temperature. And we can see, analogously to the previous slide, which was looking at pressure variations, we have 3 different degrees of shading, where the most dark shading is the solid phase being preferred. The intermediate shading is where gas phase is preferred. And the lightest shading, is where the liquid is most stable, and the lightest shading is where the gas is most stable. We also see these intersections where the Gibbs energy to temperature relationship slopes intersect one another, defining these barriers between solid and liquid stability and liquid to gas stability. We can also start to understand why some substances, such as carbon dioxide, sublime to a vapor without first forming a liquid. There's no fundamental requirement for the 3 lines to lie exactly in the same position we've drawn in figure 5.3. The liquid line, for instance, could lie where we have drawn it in figure 5.4. Now we see that at no temperature does liquid phase have the lowest molar Gibbs energy. Such a substance converts spontaneously directly from solid to vapor. That is, it spontaneously sublimates. And this is the case for solid CO2 or dry ice going straight to gas phase without passing through the liquid phase. You can see the intersection between the solid and gas phase occurs And at no point does the liquid phase actually